All right. Good afternoon, Ben, Paul, and Jehan. So let me start early today because I need to dismiss you early. Kasi meron uli kaming synchronous seminar dun sa course na tinitake ko sa University of Liverpool. At hindi ako pwedeng malate kasi meron uli kaming uh, hands-on seminar. So kailangan namin mag-join ng maaga ron. But today, we'll just keep it short because it's a little bit alanganin na because this is my last session for the course and I don't think I can cram in one meeting another method or another class of methods para sa pag-solve ng mga partial differential equations or ordinary differential equations. So I'll just think of our experience in the last part of AMAT 350 as an introduction to methods in solving partial differential equations. But there are some other methods. We only tackled the sort of finite difference schemes all throughout the how many sessions did we have? I think we had 6 sessions including today. So lahat sila ay nakadepende sa pagsulat or pag-approximate ng mga derivatives, be it partial or be it ordinary derivatives, na involved dun sa equation as a finite difference or as a divided difference, right? But there are some other techniques na mas theoretically involved, like the finite element method, which is highly used in higher dimensions. And ito yung paborito, halimbawa ng mga electrical engineers. Meron silang isang buong course, at least dun sa university na pinanggalingan ko, meron silang isang course na devoted lamang sa numerical methods. And the thing is, bihira yung ginagamit nila yung finite element of finite difference methods on its own because of the inherent instability that it has because of the very nature of the formula themselves, because this will involve division by the step size. And usually, theoretically, we want the step size to be as small as possible, but that's incompatible with what happens in machines, because if your two numbers are very small and they are within machine precision, then ang nangyayari, yung dalawang maliit na numbers ay sa paningin ng ating computers ay magkaparehas na. So there will happen some what we call cancellation errors because you're losing significant digits because of the rounding off that is inevitable in finite machines like computers. Tapos ang isa pa nga maganda ron sa course na tinake ko na yon ay Fortran pa rin yung gamit nila. And it's a first world university. And parang dati dinidespise ko yung Fortran kasi parang napaka-outdated niya. But apparently, even in the US, leading electrical engineers are still using Fortran. So ganun kaganda yung package ni Fortran para sa kanila because it's really light compared to other programming softwares. And they have developed their packages based on Fortran. So hindi na nila convert into advanced programming languages. But yeah, we also have integral approaches wherein you find weak solutions, meaning you have a differential equation, then you turn it into its integral counterpart. So that involves using Green's functions or using testing functions kung nasa sublab spaces ka and so on. That's why I'm really reluctant to start with that, which was my initial plan. Pero kasi ang daming functional analysis na kailangan bago ako makapunta doon sa topic na yon. Kaya I was constrained to really talk about finite difference methods na lamang because they are the simplest. And usually they are sufficient for applications. Mag-ingat lamang kayo dun sa non-convergence for which we have some necessary conditions, right? And then fast forward to what we had been doing last time, we were talking about the heat diffusion equation, or how heat propagate in a one-dimensional space or in a one-dimensional region, for instance, in a very thin rod. So we said that such an equation can be written in the form of equation number 1. I think my screen got stuck. Let me just restart my my share screen. So there's a partial differential equation that governs how heat propagates in a one-dimensional region, say in the region 0 to L. So we have the governing partial differential equation. and the boundary conditions, which gives us the evolution of heat at the two endpoints, to the left and to the right, at all given time. Usually, alam natin yan for all time values. So, kontrolado natin yung measurements o yung temperature dun sa magkabilang dulo. Or we have a way to measure them all throughout the time experiment. And then we also have the initial condition. What is the temperature at the entire rod at the beginning of the observation period, which we usually peg at t equals 0, right? And then we got a particular example here na kapag ka ito yung boundary conditions, ito yung initial condition, you have a rod from 0 to pi with diffusion constant 1, then this guy will be a solution for your heat equation, right? Tapos tiningnan natin paano natin madi-discretize itong heat equation. So ginawa natin, hinati natin yung space domain omega into m plus 2 points. So starting from x of 0 equals 0 until x of m plus 1 equals L. But we don't, and then the idea is to approximate the value of the solution U or the temperature U at each of the mesh points x1, x2, x3 until xm all throughout the time discretization, right? Hindi na natin kailangan tingnan kung ano yung nangyayari dun sa magkabilang endpoints because we already know or we already have the boundary conditions. So it's just finding m function values at every time step. So yun yung hinahanap natin. What's the temperature at xi, I going from 1 to m for all time values? And again, we will be implementing it in a computer, so we need to discretize the observation time as well. So say we want to observe what's the temperature over on the rod over the time interval 0 to capital T. So what we're going to do is to discretize that interval 0 to t into n plus 2 moments in time so that you have this formula for the step size. And then here's how we get the t sub j's. And our goal is to compute the temperatures at j going from 1 until n plus 2. Right? So those are our goals here. And then the technique is very similar to what we did in Euler's method. We just take the Taylor series expansion, but meron lang siyang added step kasi meron tayong second derivative in the time variable. And the nice thing about this is walang mixed derivatives. So lahat ng partials ay either partial lamang lahat with respect to time or partial lamang with respect to x. In particular, the right-hand side of the heat equation has the second derivative with respect to x. So kailangan ko ngayon ng pampalit sa second derivative or second partial derivative ni u with respect to x. And luckily, I can just naturally extend the Taylor series expansion, which you learned in your elementary calculus courses, by holding the second variable to be constants. Kasi partial lang naman or second partial lang ni u with respect to x ang kailangan ko. So hindi nagbabago yung t. Hindi nagbabago along the t dimension. So yung x lang talaga ang babaguhin ko. So in the Taylor series expansion, I will just hold the time variable to be constant. So parang function lamang siya ni x. So I'll get the expansion of u at x plus delta x and x minus delta x. And then you do the algebra and solve for the second partial derivative with respect to x. And what we get is our good old familiar 3-point centered formula of order big O of h squared or big O of delta x squared. Right? So ito yung nakuha natin formula, which you have already seen in elementary numerical analysis. And then remember the left-hand side, it has the first time derivative or the first partial derivative with respect to time. So ganun ulit, ulitin ko yung ginawa ko kaninang proseso, pero mas madali yung discretization o yung gagawin nating truncation ng continuum model into a discrete model ng left-hand side because it only involves the first partial derivative with respect to time. So kinuha ko lang yung expansion niya, all right? And then I took the 2-point forward formula. It's 2 points kasi 2 points yung ginamit ko. The function values of u at 2 time moments, right? Tapos forward siya kasi ang ina-approximate ko ay partial with respect to our value ng partial derivative ni u with respect to t at the time t, little t, right? Ang ginamit ko ay dalawang points, yung function value sa t plus delta t at saka sa mismong time t. And then it's forward because from t, I jump forward to t plus delta t. So it's a 2-point forward formula of order big O of delta t. So it's an order 1 approximation for the first partial derivative. And then we'll put these ingredients together. So remember, this used to be du over dt, right? Or the partial of u with respect to t. We scrap the continuum model. We replace it by the divided difference you see on the left. And then the right-hand side was d times du, or d squared u over dx squared. Again, we approximate the second partial derivative by a finite difference, right? And hence the name, it's a finite difference scheme, right? And then to make the writing of the formula better or easier and ready for translation into machine syntax, so I will just denote u of x sub I comma t sub j by uij. And then putting using that notation, we're gonna have this guy, and then simple algebra, we will have this. And this is what we call, or what we can call as an iterative explicit formula. Or actually, even more than that, I can say it's an iterative explicit time marching formula. Actually, pwedeng damihan ko yung adjective. It's an iterative, explicit, one-step time marching formula. Actually, may dagdag pa pala, sorry. Iterative, explicit, one-step forward time marching formula. It's explicit because the temperature value at the ith discretization point in space at the j plus first moment in time is given explicitly in terms of temperature values at the previous time step. So it's really explicit in terms of time. If there was a term here that involves the subscript j plus 1, hindi na siya explicit. Medyo mahirap na mag-solve kapag implicit yung problem because maybe the reason you cannot isolate the one with the subscript j plus 1 to one side of the equation is that you have a non-algebraic function or a transcendental function involved on the right-hand side. So, ibig sabihin, magkakaroon ka ng isang non-linear equation na mahirap ding isolve by hand. So basically, you will require some numerical techniques in order to solve non-linear equations. So sa UPLB, dinidiscuss yon sa Math 175. But again, luckily for us, we have an explicit method. It's a time marching algorithm, in particular a one-step marching iteration formula, because to get the temperature at the j plus first moment in time, we're just using the temperature values at just one previous moment in time. Ginagamit natin yung values at time t equals t sub j, right? And then what else? Explicit formula. Yeah, I think that covers everything, no? Iterative siya kasi magsisimula ka sa initial condition because here, this should be true for all I going from 1 to m and j going from 1 to capital N. So imagine here, j should be starting from, what happens when I is equal to 1? Well, when I is equal to 1, so this guy becomes 1. So this is u2j. u2j is the value, sorry, not u2j. Oh yeah, that's right. 1. Tapos ito ay 2j. So that means that's the temperature on the second discretization point at the previous time step. Tapos ito ay magiging 1. Ito ay magiging 0. Is u of 0 allowed to be is 0 allowed to be a subscript in space? Yes, because u sub 0 will just represent the temperature at the left endpoint. So okay lang yan. So, and then, but other than that, so we need an initial condition, an initial value, right? So we need u sub 0 of j. For all j values, kasi posible na, yeah, kasi kailangan ko to para ma-solve yung temperature sa x sub 1. But luckily, we have the value for this because according to our notations, this is just simply u of x sub 0 comma t sub j, but x sub 0 is equal to 0, the left endpoint. And we have the initial condition there. Ano ang variable yun? I think it's g. We just have g of t sub j. So that's fine. Similarly, that's what will happen when I is equal to m. So the complication there is going to have an m plus 1 here, but m plus 1 is just the subscript intended for the right endpoint, and we know what happens at the right endpoint for all time values. And then here, j goes from 1 to capital N. So we'll have U2 here, 1, 1, 1. Oh, everything will be fine because ang lahat naman ng subscript ay mag-start sa 1. Actually, hindi pala sa 1 siya mag-start. Ano? Dapat mag-start siya sa 0. Because I want to get also U of I1 for I going from 1 to N. So that means J goes from 0 until N, yeah, until capital N. Mas marami pala yung number of time moments na kinocompute ko. Kasi kapag kasi J ay 0, I will have U1. And it is necessary for us to compute U of I comma 1 kasi hindi natin alam yung temperature at the first moment in time after the initial observation, right? So kasi nag-start tayo sa T sub 0, which is taken care of the initial condition f of x. Pero yung first time step, yung delta T time step, kailangan natin yung computin, right? So dapat ang J talaga mag-start sa 0, but when J starts at 0, it's fine. We get 1 on the left-hand side, but on the right-hand side, we're gonna get zeros. Saan manggagaling yung U of I's, comma 0? That will be coming from f of x. Okay? So yun, medyo paki-correct pala yun. 0 siya dapat doon. And then this is iterative because we do this as I goes from, or as J goes from 0 to capital N, and for all I's. Gagawin natin to sa lahat ng I, pero iterative in J, gagawin natin to pa isa-isa kay J, sabay-sabay ma-update lahat ng I. And I think the better way to write this is via a system of equations. So we will translate it into a linear system. And that's what we're going to do today. Try to write it in matrix form, and then do it in Matlab, produce some fun animations to show us the evolution of the temperature throughout time. And hopefully that will prepare you for the problem set for this section of the course, which I already uploaded, and we can talk about it later. And there's just assignments tab ng ating Canvas page. But here's our equation. Let me just paste it here. Okay. Oops. Okay. Okay. So yan yung equation na gusto nating i-translate into a matrix. Well, it's just finding the pattern and arranging it into a nice matrix, right? So my general goal is to write it as a coefficient matrix times the vector of unknowns. But here, the unknowns will be iterative in J. So ito ay magiging U1, comma J, U2, comma J, U3, comma J, U4, comma J, until U sub M, comma J. And I want this to be equal to U sub 1, comma J plus 1, U sub 2, comma J plus 2, U sub 3, comma J plus 3, until U sub, sorry, hindi nagbabago yung naka-plus dito. So it's U sub 2, comma J plus 1, U sub 3, comma J plus 1, until U sub M, comma J plus 1. Okay? So the question now is, how do we define the right-hand side? Madali lang tong yung left-hand side. Madali lang tong right-hand side na to kasi ito lang yung nandito, right? So nilagay ko lang siya dyan, nilagay ko as a vector, right? So the problem is this, how can I represent this in matrix form, or is it possible to do that? Well, at the back of my mind, it should be, or it should be doable because the differential operator is linear, so dapat ma-model ko siya by a linear system. Kung hindi linear yung differential equation, ang usual trick ay nililinearize natin. Kinukuha natin yung linear approximation to the ODE because the idea is ang lahat sa mundo ay reducible into a linear model, or something like that. So ngayon, sige, umpisahan ko yung least value of J. Now look at the formula. When j is equal to 0, okay, so we'll have u of I1 I equals to d ng u of I plus 1, 0, plus 1 minus 2d, uij. This would be I0 plus d ng ui minus 1, 0. Now, okay, how will they fit into this system? Well, ang sabi rito, halimbawa, kapag kasi I ay equal kay 1, kasi kukunin ko yung first row nito. So pagka perform ko yung matrix multiplication of the first row times this guy, I am supposed to get u sub 1 comma j plus 1. Pero to get u sub 1 comma j plus 1, so u sub 1, j plus 1, so I is replaced by 1, I will need d times u sub 2 comma 0. 2 comma 0, j equals 0. So meron ako ditong, okay? So ibig sabihin, ito, dapat ma-multiply by d. So I'll have d here in the second column of my matrix, first row. So first row, second column of the coefficient matrix will be d, kasi kailangan ko ng d times u2, comma 0, kasi nga ang j natin ay 0, ang I ay 1. And then when I is equal to 1, ano nang susunod? So I'll have here u of 1, comma 0. So u of 1, comma 0 should be multiplied by 1 minus 2d. Okay. So yun yung nasa first row, first column. And then the last thing is this guy. Ito ay maging u0, comma 0. Pero I don't have a u0 in my coefficient matrix. But I am desperate to have a d times u sub 0, comma 0 into the mix so that I can get u sub 1, comma y, u sub 1, comma 1. All right. So that means merong extra add-in dito sa right-hand side. So ito ay merong plus d times u of 0, comma j. All right? Kasi ganun din yung mangyayari kapag si j ay equal kay 1, ito ay magiging 2, ito ay magiging 1, ito ay magiging 1. There we go. When I is equal to 1, I will need u comma 0, u sub 0, comma 1. And that will be given by that term over there. I cannot insert it inside my coefficient matrix because I'm reserving the vectors there to only involve temperature values at the m discretization points that are internal to the interval. Okay. Tapos ang huli na, wala na pala. So lahat ito ay zeros na. Okay. And then when we go to, hindi pala dapat kay J ako nagano para mas makita yung pattern, ano. I should have played with I. So when I is equal to 2, so we'll have u sub 2 comma j plus 1 equals d times u of what? It's going to be 3 comma j plus 1 minus 2d u sub 2 comma j plus d u sub 1 comma j. So u sub 2 comma j plus 1 will be yeah, this would be here. So kailangan i-address ko yung second row. Right? So para magkaroon ako ng second row, okay, for the second row, I need d multiplied to u3j. U3j is the third entry in the column vector. So I should have an entry in the third column of the second row. And then I need a 1 minus 2d multiplied to u2j. U2j is the second entry. So the second entry in the second row should be multiplied by 1 minus 2d. Okay. And then the third would be u1j. Siya yung nandito sa unahan. So dapat meron ako ritong d. And then it will be 0 elsewhere. And this guy will also be 0. Kasi wala ng extra term para sa kanya. You can do it a couple more times to see the pattern, but spoiler alert, yung pattern dito ay meron lamang akong tri-diagonal entry na yung main diagonal. Ang laman ay mga 1 minus 2Ds. Tapos yung dalawang off-diagonal entries, puro D yung laman. Tapos 0 na siya elsewhere. And then this vector to be added to the product will have 0 entries in the middle, but yung huli niya ay merong D times U sub M plus 1 comma J. Okay. And so this would be the matrix form for our FDS or finite difference scheme, right? So we can call this, let's call this matrix A, because this matrix A doesn't depend on the step size, really. It only depends on the constant D, which is basically, nakadepende pa rin siya sa step size H, ano? Pero hindi siya nakadepende dun sa time value. Kung nasa ang moment ka man in time, yung matrix A hindi nagbabago. Because the matrix A only depends on the constant D, but the constant D, remember, is just the diffusion constant times delta T over delta X quantity squared. So hindi siya nakadepende sa times. Tawagin ko na lang siyang U. Pwede nyo siyang i-store kasi forever yan naman yung U natin na gagamitin. Now, this guy is another story. This is U, but it depends on J. So I'll call it U upper J. Para lang i-denote na ito yung vector consisting of the temperature values for all of our discretization points at time t sub j, right? And then plus, I'll add to it a vector v. Tawagin ko tong vector v na dalawa lang yung non-zero entries, yung una at saka taas, which makes sense because remember, para makuha yung temperature at a particular moment, at a particular point in our space, kailangan mo yung dalawa niyang kapitbahay. So kapag si x, pag si I ay equal kay 1, kailangan natin yung x sub 0 palagi. At kailangan ko si x sub 2. Wala tayong problema kay x sub 2 at saka si x sub 1 kasi nandun sila sa vector u upper j. Pero yung temperature sa x sub 0, wala siya dun sa vector u upper j, kaya iniiwalay ko na lamang siya. And the same thing goes when you are at the second to the last point, x sub m. Sa x sub m, kailangan mo pa rin yung dalawa niyang kapitbahay. So you need the temperature at x sub m minus 1 and x sub m plus 1. But I didn't include the x sub m plus 1 into the vector of unknowns because I know beforehand what's the temperature at x sub m plus 1 for all time values, for all eternity. We do have the value for the temperature for those boundaries. Kaya naman, eto, doon lang yung dulo lang yung meron. Otherwise, yung mga interior points, wala na nanggagaling sa kanila kasi yung tatlong nagko-contribute dun sa temperature at the next time step ay nandito na sa matrix, alright? Laging tatlo yung added. Okay? So we have the constant matrix capital A, I mean constant with respect to the indices J and I, right? It's a tridiagonal matrix and hence it can be shown to be invertible with a similar argument as what we have seen before. Kaya lang, hindi naman tayo nag-i-inverse problem. So that will not be a big issue. And then this vector also depends on J pala. So let's call it V upper J. That's the temperature or the vector containing the temperature data at the boundary points at all discretization moments in time. And this is equal to this vector U upper J plus 1. Okay. Lipat natin ng konti. Okay. Okay. And there we go. This is the matrix form for our FDS. Okay. And we do this, J going from 0 until capital N. Para madrating natin yung T sub N at T sub N plus 1. Which will be basically our capital T, right? And yeah, and it shows that our approximate to our ODE is simply just a multiplication of a matrix. Isn't that amazing? Yung problema mo kanina, na differential equation na usually mahirap i-solve by hand ay na-reduce natin into a simple matrix multiplication problem, right? Actually, now you can play a little bit more here. Kung gusto mo mag-inverse problem, pwede mong isulat to as AU upper J equals U upper J plus 1 minus V upper J, all right? If you desire a certain temperature at a particular, at the final time capital T, pwede mong isolve na lang kung ano dapat yung initial temperature via backward iteration para makuha mo ano dapat yung initial condition para ma-attain ko yung temperature at the run. Alright, yun yung parang inverse problem na method. Tapos ang solution nyo lang, solve mo lang to for the vector u. So mag-apply ka lang ng A inverse both sides. Yun yung mas mahirap na problem, yung inverse problem, kasi medyo mahal mag-invert ng matrix. Pero ang kagandahan dito, constant yung matrix A, hindi yan nagbabago. Ang nagbabago lamang ay yung right-hand side kasi nag-iterate tayo through time, right? So pwede mong isipin yung U upper J plus 1 to be your desired temperature at time T at time capital T. So you might know this is your target temperature. You know this because V upper J is just the temperature at the boundary, so you can assume you know what the temperature at the boundaries are. And then, so ito ay constant. Tapos, kukomputin mo lang, so U upper J ay equal lamang sa A inverse times U upper J plus 1 minus V upper J. Alright? Tapos makukuha mo si U upper J. So pwede itong maging U upper J, tapos ito magiging U upper J minus 1. Another inversion will give you U upper J minus 1. You do it sufficient number of times, yung matrix inversion na yon, you're gonna get U upper 0, which is which is a sufficient initial condition para ma-attain mo yung desired temperature mo at U upper J plus 1. Pero that's a highly unstable and a very costly process because matrix inversion is much more expensive than matrix multiplication. Pero ang kagandahan nito, si matrix A hindi nagbabago. Ang nagbabago lang kada iteration ay yung right-hand side. And for Ben, Paul, and Ivy, nakita na nila ito dun sa AMAT 255 na may madaling paraan kung paano mag-solve ng mga linear systems na paulit-ulit lamang naman yung coefficient matrix. And that's via matrix factorization. You can decompose A into an into a product of a lower and upper triangular matrix, or you can write A as in QR decomposition, a unitary matrix and a rectangular matrix. What else? You can do Cholesky, you can do Kraut, and so on. Pero I was going off topic there just to bind the two, to weave the two courses together. But really our goal is not this one, but to solve the yellow problem. Kasi dito, forward problem yung sinosolve natin. Alam natin yung boundary conditions. Alam natin yung initial condition. And our goal is to find what's the temperature profile all throughout the rod at time capital T, which is basically x sub t comma n plus 1 for all x in omega. At least in omega, because we already know the temperature at the boundaries. Okay? So yun yung goal. And madali lang siyang i-implement sa computers. But before we go to a machine implementation, we should take note that there are some conditions for this iteration to converge. Hindi magko-converge itong method na to sa basta-bastang choice ng step sizes, because that's the only degree of freedom that we have here. We have the degree to choose, or we have the freedom to choose what's the time step and what's the step in the spatial domain. Ano yung delta x at delta t? Well, there's still holes in the theory of finite difference schemes, and yung pinakamadaling paraan to somewhat increase the probability that our method will converge is through a necessary condition, which we call the Courant-Friedrich or Friedrich-Lewis condition, or the CFL condition, right? And it usually varies from problem to problem and from the type of FDS scheme that you have, right? So medyo magkaiba kapag ka explicit o kaya implicit yung FDS mo. Nakadepende din siya kung anong klaseng equation yung meron ka, kung elliptic PDE yung meron ka, kung parabolic yan or elliptic yan. Iba-iba yung CFL conditions, right? But just remember that CFL is not a necessary and sufficient, it is just necessary. So hindi siya sufficient. Meaning, if the FDS or the finite difference scheme, let's call it, did we number our FDS already? Hindi pa pala, no? So tawagin natin itong 2. Let's call this equation 3, right? So if the FDS 2 or 3 converges, then the following bounds or the following inequality is true. So 2D times delta T over delta X quantity squared is less than 1, right? This constant, which we require to be less than 1, is what we call the CFL constant. So if this inequality is not met, then we are sure that the finite difference scheme will not converge because the attainment of this inequality is necessary for convergence, but it is not sufficient. And also, just to increase our chances of getting a convergent scheme, dapat mag-guarantee natin to. Little d here is, hold on, is it little d? I think it should not be little d. It should be capital D. Sorry about that. This is capital D. Yung diffusion constant siya dapat. Okay. So it's 2 times capital D times delta over delta x squared should be less than 1. In our particular problem, madali lang yan. Delta t over delta x quantity squared should be less than 1/2. All right. So you can find some readings kung bakit ganito yung Courant-Friedrich-Lewis condition, but it will require some other functional analysis stuff. So I will skip the proof, and that's for you to research on. All right. Pero ito yung kailangan nating i-guarantee para may chance na mag-converge yung ating method. Right. Again, that's capital D. This is the constant. This is the constant that shows on the right-hand side of our heat equation. Okay. Now, any questions? I think I finished everything that I want to write on the board. Punta tayo sa Matlab. Okay lang ba? Any questions? Okay, so if there are none, punta na ako sa Matlab. Parang tahimik kayo. Or na-sense nyo na nagmamadali ako. Kaya hindi rin kayo masyado nagre-react. Okay. Let me just clear everything here from my side. Okay. Let me share my screen. Okay. So I'll share with you later this code. Pwede nyo siyang ma-download from the modules page ng Canvas later, after my class siguro by 7 p.m. I'll be able to share this with you. And you can use this as the basis for the code that you'll be writing for the problem set. I'll just walk you through my idea when I was writing this code for the heat equation. Simple lang naman to, and you can actually find better ways to write the program. It's just something that I wrote on the fly when I was doing my math 191 class. So live kaming nag-code, and usually pag nagko-code ako, yung shortcut muna. Tapos pag matagal siyang hindi shortcut. Yung unang pumasok sa isip ko na way of writing the code, yun yung sinusulat ko. Tapos pag masyado siyang matagal mag-run, saka ko siya ino-optimize. Saka ko tinatanggal yung mga redundant steps, saka ako nag-vectorize, saka ako nagpa-parallel computing, and so on. But if there's no need for it, then hindi ko na siya ginagawa. All right, let's see. So line number 4 simply declares to Matlab that the variables x, t, and y should be reserved to be symbolic variables. So pag nakakita si Matlab ng x, t, and y, alam niya na ito ay mga para sa symbolic functions. All right? Hindi niya yan hahanapan ng value. Hindi sila yung usual variable handles kung saan nag-assign tayo ng value within the program. They are indeterminates, kumbaga. Kung sa algebra, ito yung mga indeterminates ng polynomials. So they should be treated as function handles, or not function handles, but symbolic variables talaga. All right? Now, this is a code for inversion, so meron diyang question about regularization. So don't mess with line number 7. Keep it 0. Actually, kahit baguhin nyo, walang effect kasi gagana lang yan kapag tinurn on ko or in-uncomment ko yung lines 139 until line 203, right? Kasi yung mga lines na yun ay para sa inverse problem. Pero forward problem lang naman yung sinosolve natin. So, dun lang tayo sa unang part ng code. And then I have here a question whether you want to produce an animation or not. For now, let's turn it off. So, i-zero ko muna siya. I-1 nyo siya kapag gusto nyo mag-produce ng animation on ng GIF. Ano? And then lines 10 to 12 supplies Matlab with the constants or the parameters in our problem. The terminal point in the space domain is pi. The terminal point in time is 1. And then the diffusion constant is 1. So ito yung sample problem na pinakita ko sa inyo last time na may initial conditions as alam ko yung actual solution. All right. So here the initial condition is the function f, which is 10 sine 2x. Now, usually, if I run this on its own, Matlab will produce an error because it will be looking for what's the value of x. Ano yung x na ipa-plug in niya para ma-compute si f. Pero remember, in line number 4, I declared x to be an indeterminate or x to be as a symbolic variable. So Matlab will not complain kasi alam niya na pagdating niya sa line 15, si x pala symbolic variable. So alam niya na ngayon, symbolic variable siya. So si f inherits the variable type of x. So si f then ay magiging symbolic variable. And then I want to do that also for the boundary conditions. Kahit dun sa problem na pinesent ko last time with the specific conditions, yung boundary conditions niya ay 0. 0 yung temperature dun sa magkabilang dulo all throughout the time interval. All right. So pwede mo siyang itilita sa constant, pero in preparation, pagka binago ko na yung boundary conditions, posible na silang maging functions ni t. Kaya sinulat ko siya dito or sila dito as if they are functions of the time variable. Tapos sa line 18, dineclare ko yung true function f or the true solution function u. At yung true temperature, tinawag ko lang siyang f for whatever reason, but this is the true function at the particular time capital T. Kasi yung solution, if you remember from last meeting, ang pinakita kong example na solution ng heat equation ay T times e to the negative 4t times sine of 2x. So ito ay little t dun sa solution natin. Pero we're plugging in capital T. So ito yung temperature, ito yung true temperature. Ito yung exact temperature at time little t equals capital T. Right? Tapos sa lines 21 to 22, pinili ko ano yung spatial size ng spatial discretization at temporal discretization. So ibig sabihin, ilang interior points yung gagamitin ko. So I'm telling here, Matlab, you're gonna use 10 internal points in space. So magiging 12 yung points na gagamitin kasi 10 plus yung dalawang magkabilang dulo. And then sa temporal discretization, 122 yung kakalabasan niya. Or actually 121 lang siyata. Kasi kasama si 0, kasi capital T na yung nasa dulo. And then Matlab will compute delta x and delta t. So that's what you have in lines 24 and 25. And then I have a quick check here if CFL condition is met. Kapag lumampas sa 0.5 yung dt over or yung delta t over delta x squared, then the forward solver will not converge. Kasi necessary condition nga pala yung CFL natin. All right? So pag binigyan ko kayo ng ibang equation, mababago rin itong CFL condition nyo dito. All right? So para may pan-check lang, tama ba yung sinelect ko na capital M at capital N? Because otherwise, you need to adjust capital M and capital N. Okay. And then ito na, i-discretize ko yung X variable, yung X domain at saka yung T domain according to the step size delta X and delta T. And then this guys, ito yung ating vector consisting of function values at or temperature values at x sub 0, at yung temperature values at x sub n plus 1, then this is the these are the temperature values at time t equals 0. Binectorize ko lang sila. Alright? So you can read later kasi wala na akong oras, ano? Yung subs, ito yung nagsa-substitute ka na. So ang ibig sabihin nito, magsa-substitute ako kay function g, kay symbolic function g, etong mga inputs na to, right? So remember, g is a function of t, so MATLAB will plug in the contents of this vector into the function g, and then I will convert whatever that symbolic vector is into a double precision vector. Okay. So, by the way, if you can go through the MATLAB code. If you have questions, we can schedule a meeting next week if you want and consult kung paano nag-work itong program ito. But I'm really running out of time, right? So, pasadahan ko na lang na mabilis, ano? So, itong for loop na to, ito yung nag-define ng matrix capital A. And then this computes U. So, ito yung A times U upper J minus 1 plus V upper J minus 1. Yeah, so ito yung A times U upper J minus 1 plus V upper J minus 1. And it will give us U upper J. Ito yung iteration formula natin as part of a matrix. And then U part will be a matrix with each of the rows corresponding to temperature values for each of the discretization points, and the columns represent the temperature values at the discretization points at particular moments in time. So yung bawat column dyan, yan yung temperature reading at a particular time t sub j. Tapos inassemble ko lang yung buong time evolution matrix, capital U. Kasi yung U part, siya lang yung nandun sa interior. Hindi kasama si T sub 0 at saka actually si T sub 0 lang yung hindi kasama kasi kasama na rin si T sub n plus 1. Because the iteration here goes from 2 until n plus 1. So kasama na si T sub capital N plus 1, which is capital T. Tapos, ito yung, this figure will generate what's the predicted temperature at the terminal time. So this is what you will report. And then here it's a comparison between the 3D plot of the actual solution and the estimate solution. And we can do that because we have an evolution vector, an evolution matrix capital U. Tapos, pinaplot ko rin magkahiwalay, exact solution in the 3D space. Tapos interpolated the estimate from the finite difference scheme. Tapos meron ako ritong computation ng relative error. Relative error lang to dun sa final time capital T kasi dun lang naman ako interesado. And then I have here the code for the animation. Now, dahil wala na talagang oras, isabayin ko na, i-run ko to with animate equals 1 para makita natin yung time evolution. And then here's what will happen. So I pressed F5. Nag-compute si Matlab. Tapos ito, papakita niya yung time evolution. So the orange or the red line is the red curve is our estimate, and the blue one is our exact solution. So graphically, or at least visually, you're seeing how the temperature readings evolve through time. So parehas yung exact solution saka yung estimate solution. If you look at the title of the figure, I have here I have there the time label. So nasa time 0.33 seconds tayo. And then I also have the relative error. Ilang percent yung error all throughout. This is the L2 relative error. I'm getting the L2 norm of the difference between the true solution evaluated at the mesh points minus the computed solutions divided by the norm of the computed solution. Okay. And it makes sense that as time goes by, lumalapit kay 0 yung temperature reading. And that's the very nature of temperature, right? There's no external source of the temperature here. We said na meron kang temperature, may initial temperature ka na 10 sine 2x. There are no heat sources within the domain omega. The boundaries have very cold temperature, 0 degrees, yung nandun sa magkabilang dulo. So ibig sabihin, malamig sila. So understandable na yung 10 sine 2x na temperature in the absence of an external source will decay to 0. Right? So kung masyadong malayo yung time evolution dun sa animation, pwede nyo i-off yung pwedeng hindi nyo i-fixed yung hindi nyo i-fix yung y-axis. Punta lang kayo dun sa animation code, line 110. Tapos i-comment nyo lang yung y-lim. Nilagyan ko yan ng y-lim para hindi nagbabago yung y-axis para makita natin yung pagbaba ng amplitude ng mga curves. Pero pag kinoment nyo yung mga y-lim sa lines 119 and 126, see what will happen? So, binibigay ni Matlab yung best view insofar as the curves are concerned. And look at the y-axis. The y-axis is automatically adjusting based on the amplitude of the curve at a particular time t. So kung ayaw mo nung masyadong lumiliit yung scale o yung amplitude para makita mo magkamukha ba yung estimate ko at saka yung actual solution, then you turn off the restriction on the y limits para nag-evolve o nag-adjust yung scaling sa y-axis. Okay? And then other information that I got from this code, oops, sorry. Yun lang pala. Okay. Kasi pagka nag-minimize ako ng animation plot, ang itatry ni Matlab ay patungan yung current figure. So doon mag-play yung animation. Kaya wag niyong i-close, wag niyong i-minimize yung animation kasi papatungan niya yung mga existing figures. That's why gusto ko minsan i-off ito para makakita ng still pictures, right? So ziniro ko yung animate. So magkakaroon pa rin ako ng mga figures. Pero ito yung makikita ko. So ito yung three-dimensional plot nung interpolated, nung estimate natin mula sa FDS. Tapos ito naman yung exact solution. So you see here that they look similar. So pwede mo yung paglaruan, rotate mo, right? So you can look at slices. Medyo understandably smooth yung solution, all right? So pero medyo jagged yung ating approximate, right? And that's understandable kasi nag-discretize tayo. So parang ang ginawa ni Matlab dito, nag-connect the dots siya. So I don't know what's the internal routine that Matlab used to interpolate between 2 points, pero baka naman nag-ano lang siya, piecewise linear interpolation. So literally nag-connect the dots lamang siya via straight lines. So that's why you get jaggedness in the in our estimate. If you want to smooth this out, pwedeng liitan mo yung delta x. Pero that means you need to check whether the CFL condition is still satisfied. So you can play with it. Then what I also did is to plot them on top of each other. Tapos dito medyo, kita ko na. Pag pinagpatong ko yung dalawa ng curves, I will see very similar results. Pwede ako mag-zoom in. Masyado silang magkalapit na yung pag-zoom in. Hindi ko na nakikita masyado kung ano yung nangyayari. But yeah, there we go. There seems to be a disconnect between those two. Nakikita ko pa rin yung jaggedness noong actual solution. Okay, so I need to stop here. Pero may isa pa palang figure. Ito yung two-dimensional plot showing us the temperature prediction at time t equals 1, right? So play with the code and then let me know siguro tomorrow or on Monday if you have some questions about the code, because I want you to use that as a stepping stone for the problem set. Meron pa akong 5 minutes siguro. Right. So flash ko lang yung problem set natin. Medyo delayed yata. So naka-upload na to. So gusto kong i-replicate nyo yung ginawa natin all throughout the last 2 sessions or last 3 sessions, but this time for the convection for the convection diffusion equation that you see here in equation 1. So kamukha siya nun, except that there's an additional term on the left-hand side, which is a constant little a times the first partial derivative of u with respect to x. Tapos nagbigay ako rito ng value ni A at saka ni alpha at saka yung terminal time value capital T. I gave you the initial conditions or the boundary conditions rather in equation number 2 and the initial condition in equation number 3. Tapos ang gusto ko ngayon, gumawa kayo ng parang isang journal article na magdi-discuss ng development ng finite difference scheme para dito sa specific convection diffusion equation system 1 to 3, right? So you write it as if you're writing a research paper, but of course this is not a big deal kasi parang classroom problem lang siya, pero I want you to package it in a way that mimics a journal article, all right? Tapos, yeah, with the usual contents, all right? And then those recommendations and conclusion, I want you to say something about what we call the Crank-Nicholson method. So that's a reading assignment for you. What's the Crank-Nicholson method and what it offers insofar as improving finite difference schemes? How it is done? It is really a quick extension, you know? So pwede nyo siyang i-discuss. So parang reading assignment na siya and incorporate it as a recommendation in the paper that you'll be writing. You can write one way to improve the accuracy of the finite difference scheme is to use the Crank-Nicholson method, specified as follows: a short description of the Crank-Nicholson method, and then mention what are its advantages. So pwedeng mag-cite na lang kayo ng sources. Wala na kayong derive. Cite nyo lang yung sources and write it in your own words. Tapos in crafting the mathematical and numerical framework and the results and discussion section, you can follow the following steps. Ano? So una, verify nyo muna na ito ay true solution. Tapos mag-derive kayo ng explicit finite difference scheme. Ano? So dun sa first order partial derivatives, gagamit kayo ng two forward difference formula. So alam nyo na yung partial with respect, yung partial ni u with respect to t. So ganun din, kamukhang formula yung makukuha nyo for the partial derivative of u with respect to x. And then you should also use the 3-point centered formula for the second order partial derivative, which you already have. So isa na lang talaga yung kulang. And then write it in an iterative formula format and the matrix equation. Tapos kailangan yung mag-search sa literature. So you do a combing of related literature and see what is the existing CFL condition for the one-dimensional convection diffusion equation. Properly cite your source and use that as guidance para sa pagpili nyo nung delta x and delta t para dun sa number 4. Sa number 4, ayun, irarun nyo na yung Matlab code nyo, papakita nyo sa akin gano'ng kaganda yung estimate nyo at time t equals 1. You can include three-dimensional plots for the entire time and the space domain. You can show me the figure, compare the two-dimensional figure showing the temperature at time t equals capital T over the entire team rod 0 to 1. All right. Tapos, pwede nyo rin computein yung L2 relative error just to give an analytic sense of how good the approximation is. Okay. Tapos, gusto kong ipakita nyo or illustrate nyo na magda-diverge yung method or hindi siya magiging malapit dun sa actual solution kapag ka hindi na-satisfy yung CFL condition. All right? So I really need to go, so sorry about that, guys. But let me know via email or via chats at Teams if you have some problems about it. And if you want, we can schedule an online consultation so that I can guide you in your problem set, or if you have some questions about the Matlab code. So kung kailangan nyo too long, just let me know. I might be available also for some limited time during the Christmas break, so just let me know. Don't hesitate to send me an email. The deadline for the problem set is tentatively scheduled January 7, but just let me know if you need extension. So pwede kong extend siya hanggang January 11, okay? So with that, guys, thank you for joining me not only today, but for the past how many weeks, 2 or 3 weeks. Hopefully you got something from this section of the course. Good luck on the remainder of the semester, and I'll be waiting for your emails and questions, all right? Bye, guys. Have a good one.
Thank you, sir.
Thank you, sir. Bye-bye.
Hi, sir. Sir, may class pa po next week kay Sir John?
According sa calendar, meron pa si Sir Joms yung magana.
Okay po, sige po. Thank you, sir.
All right. Sana may libreng Matlab. Oo nga, andali kasi pag Matlab eh.